This technology was deployed, used successfully, and then stalled out. We've come up with a set of very low-cost, earth-abundant materials that allow us to produce this battery at a cost point very similar to where lithium-ion is headed.
This is EnergyCast, and I'm Jay Downhauer. Today we are talking about metal hydrogen batteries, a technology we sent up into space decades ago and then essentially forgot about until now. My guest says they've taken the core principles of the technology, creating hydrogen when charging, converting back to water when discharging, and updated it for our new energy landscape. Engineers who developed these batteries in the 80s and 90s had no idea how reliant on renewable energy and the storage to back them up would become in the 2020s. Utilities are looking everywhere for reliable, affordable, high-capacity battery backup. And with many utilities making carbon-neutral pledges, they'll need all the storage they can get. My guest is proud of the advantages metal hydrogen batteries could bring to the conversation. They are maintenance-free, good for tens of thousands of cycles, and can respond quickly to energy needs. But the Reagan-era predecessors were expensive. They used a lot of rare earth materials and had expensive catalysts. The big innovation my guest and his team made was using more abundant materials like nickel and iron. My guest says this was the key to bringing this family of batteries back into the conversation. The only drawback is their weight. These batteries were bulky then and are bulky now. Ironically, they'd be the last kind of batteries you'd send back into orbit these days. But down on terra firma, weight isn't that big an issue. My guest says they'd be ideally suited for a stationary setting beside a solar farm or a substation. He says there are several advantages over lithium-ion, and even if they're heavier than lithium-ion, that's okay. I believe all these batteries and storage families have a unique place for our energy future. Lithium-ion for cars, metal hydrogen and flow batteries for on-site storage, for instance. There are going to need to be a lot of tools for a cleaner, more reliable, and more prosperous energy future. My guest today is Jörg Heinemann, CEO of EnerVenue, a Bay Area battery developer specializing in metal hydrogen technology. EnerVenue was launched in 2020 as a spin-off of co-founder and Stanford professor Yi Shui's Enotech startup foundry. Jörg joined the group last June, having spent several years in the solar sector. That August, EnerVenue announced a round of funding in excess of $12 million, and Jörg says the money has been put to good use, with the company claiming to be ahead of schedule on their path to commercialization. I hope you enjoy my conversation with Jörg Heinemann. We're here with Jörg Heinemann, CEO of EnerVenue, and Jörg, your battery technology is called metal hydrogen, which is different from lithium-ion. So how so?
Yeah, pretty substantially. It's different from lithium-ion. It's also different from a nickel metal hydride. What we have is a technology that was conceived back in the 1980s and deployed very successfully in the 90s for use in aerospace applications, specifically satellites, the International Space Station, Hubble Space Telescope, that sort of thing. At the time, aerospace industry was looking for a battery that could withstand the rigors of outer space. Think a battery that could withstand extremely high temperatures up to 60 degrees Celsius, extremely low temperatures down to minus 40, cycle essentially forever. And then perhaps most importantly, do it without requiring any maintenance whatsoever. So this is a true install and forget. Imagine shooting a battery up in outer space. You can't maintain that thing or augment it or replace battery packs without doing a spacewalk. So that was the use case. And it was deployed in the 90s. These batteries worked very successfully for over 3 decades, I think in excess of 100,000 cycles in some cases, but they were super expensive. Now they're really different from lithium ion. It's a completely different principle. Basically, the battery stores energy. When you charge it, a hydrogen evolution reaction runs, which builds up hydrogen inside the vessel. And in discharge mode, the reverse happens. That hydrogen gets reabsorbed back into water. The nature of that chemical reaction is fundamentally different from other battery technologies, and it allows for very flexible power characteristics. It's also very very fault tolerant in that it absorbs an overcharged state or an overdischarged state quite flexibly and doesn't build up the dendrite formation and things that eventually degrade most batteries.
The batteries we're using in the space program, why did NASA prefer these batteries?
The aerospace use case is extremely difficult to meet. How do you put a battery into outer space that lasts forever and withstands those harsh climates and requires no maintenance? At the time it was conceived, lithium-ion batteries had a maximum cycle life of about 200 cycles. That's one a day for 200 days. It would never have made it. Today, 30 years later, lithium-ion is roughly 3,000 cycles, so roughly 1/10 the cycle life. They needed something that would meet this use case. Now, it did. It did it really successfully. However, it was an extremely high cost battery. Think in excess of $20,000 a kilowatt hour. So think a boutique battery for a niche use case, and you probably wouldn't repeat that today. We think we can be very competitive on CapEx with not just today's prices, but with the future downward trend, and then win on a different capability and a very significant economic savings in terms of no operations and maintenance cost.
Was there a breakthrough that led to these types of batteries being used now more widespread, perhaps?
We've taken out all of the high-cost components, replaced it with very low-cost materials based on work that our founder, Professor Yi Shui at Stanford, did with his research team there. We've come up with a set of very low-cost, earth-abundant materials that allow us to produce this battery at a cost point that will have an upfront capital cost very similar to where lithium-ion is headed. This technology was deployed, used successfully, and then stalled out. So 10 years ago, when I got into solar and a lot of other battery technology companies took off, I think we all expected solar and storage to take hold roughly at the same rate. Storage was much lower on the uptake, maybe 10 years behind. And I think the industry essentially ignored metal hydrogen because of the cost. That, and then the folks that had worked on it 3 decades prior are probably all retired. These are companies like Saft and Eagle Pitcher that had worked in conjunction with NASA. They weren't around. The breakthrough really was in kind of dusting off this old technology and then coming back at it from first principles, saying, all right, what if we use this chemistry? What if we use this super durable nickel cathode hydrogen evolution reaction? It's almost like a fuel cell concept, but redesign it for low cost. Take out the catalysts that were extraordinarily expensive and then rethink the overall form factor and design for massive, large-scale assembly manufacturing and therefore low cost. And that's what we're doing.
You're going to talk a lot about energy storage, and I think lithium-ion batteries are great for vehicles because they're light. But I've talked to flow battery folks and others who say if you don't need to carry them around, right, you don't need the weight benefits lithium-ion batteries provide. Is there a weight benefit here, or what's the main driver for these batteries?
Our batteries have a unique combination of very flexible power characteristics. If you think about a lithium-ion battery, in addition to being light and portable, it's also really flexible from a power and energy standpoint. We've all come to appreciate that we can charge our cell phones, our electric power drills, or our electric vehicles pretty quickly. And then we can discharge that power quickly or slowly depending on what we need. That variability, that flexibility is really important, not just in these portable use cases, but in stationary ones as we look at where the grid is likely to transform to. Our battery does that. So we're very similar on a power characteristic standpoint. That's different from most non-lithium-ion technologies. So picture use cases, whether it's renewable integration, solar plus storage, hybrid in a desert climate where the battery asset lasts as long as the solar panel and there's no moving parts.
Is it as light as lithium-ion batteries?
No, I mean, theoretically, I guess you could tow the battery in the trailer behind your Tesla if you want to, but I wouldn't recommend it. It's a stationary battery. It's significantly heavier. It's bulkier. It's got a larger physical footprint, but it makes up for that. For stationary use cases, there are many of those that are not very space constrained. They're somewhat space constrained, but not very, and we're an ideal play for that.
Sure. And what sectors are you looking at right now? Like solar storage? Definitely some sort of stationary storage, right?
It's essentially anything stationary. However, the economic case for our battery is significantly better the more a customer wants to cycle the battery. So think something that requires daily cycling or even maybe twice or even 3 times daily cycling. So for example, for what I call a 24/7 solar plant owner, that's someone who's building, say, a 100 megawatt solar array coupled with a large battery, say 200 megawatt hour battery, that can do a combination to produce power during the solar day, have excess power to be able to charge a battery, and then dispatch that battery through the night and evening hours to essentially cover a load profile on a 24-hour basis. That, you could say, replaces a peaker plant. It probably even replaces base load in sunny locations. Those types of plants are being developed around the world. We're an ideal battery for that. Most of the use cases are today based on, say, a once-a-day charge-discharge cycle. In and of itself requires a pretty robust battery. And because we have zero maintenance costs, we can offer the customer roughly a 20% levelized cost advantage at a plant level, maybe a 40% levelized cost advantage just considering the storage component. That's pretty impressive. Let's say the regulatory environment changes and that customer now suddenly wants to move to 2 charge-discharge cycles per day. Maybe they want to do an off-peak energy arbitrage using wind power at night. With our battery, they can do that no problem. If they're locked into a lithium-ion solution, they've got a significant challenge, probably voids the warranty, the maintenance expense goes way up. The difference is the project return likely nearly doubles using our battery and future-proofs them against changing circumstances. I'm pretty certain, though, that the market is going to want more and more batteries that behave like our cell phones do, charged quickly when there's excess power available, and then be dispatched fast or slow as many times as you like without restriction.
The battery technology that this reminds me of the most is flow batteries. Heavier, but much more cycles, less maintenance. Do you consider that the main competition for the needs that you're trying to address?
Yeah, not so much. The better flow batteries would probably argue that they have a technology that can compete with ours. The big difference is maintenance. Flow batteries, there's a lot of moving parts. You've got pumps, you've got liquid that's flowing, you've got filters and membranes that require a replacement. Best case, very complicated devices. And there's a maintenance tail there. I think it's very difficult to make a case that flow batteries have less maintenance than where lithium-ion batteries are today and where they're likely to go. That's an uphill battle. Our battery is installed and forget, period. Also, our physical footprint is, while larger than lithium ion, it's significantly smaller than, I believe, even the most space efficient flow battery out there.
Yeah. You talked a lot about cycles. Again, you said 30,000 cycles?
30,000. That would be 3 per day for 30 years.
Sure. And what would happen at the end? You say they're maintenance free. Would you just completely replace them, or say you want to keep that same site after even 30 years?
Yeah, I mean, you certainly could refurbish it. Frankly, that 30,000 is likely to be a minimum. And I think we've seen with the legacy chemistry that can extend as long as 100,000 cycles. Perhaps more importantly, from how project owners are considering batteries these days, is our battery. It's a very simple device. Basically, it's a stack of electrodes compressed together and then placed into a sealed pressure vessel that's welded shut. It's very easy to assemble. Think maybe 20% of the tooling capex for equivalent volume relative to lithium ion. It's also really easy to disassemble, and therefore it's also very easy to recycle. At the end of its useful life, you would most likely recycle it, and that's as simple as removing, by, in this case, cutting the vessel apart, and then you disassemble it into its piece parts. It's almost like disassembling the Lego block. You could refurbish the battery if you wanted to, or you could just simply reuse the components for some other purpose.
It sounds to me like the metals are pretty common. It's not like lithium ion where a lot of these batteries require cobalt, right?
That's right. There's no cobalt, there's no lithium, there's no vanadium, there's no platinum, none of these exotic materials. The materials that we're using are available. I think it's on every continent in quite a bit of abundance. We're not supply constrained in the same ways that most battery manufacturers are.
I believe you said nickel, iron, right?
There's a lot of nickel. That's the primary component, nickel, and then there's steel. It's those types of things.
I always ask this with the people who are involved in battery storage. Where do you want your batteries to be? Utility scale, this idea that you would have them on their own separate energy storage farm or co-located with a solar farm. We see an awful lot of that. Some sort of hybrid at a substation. A lot of people are interested in having a battery that's in your home. What are your thoughts about that?
Yeah, it's all of the above. Our battery is well suited for any stationary use case. What we're aiming for initially, because what we're doing is taking a new technology and launching it into hyperdrive. We want to reach gigawatt hour production capacity within 24 months, which is a very, very steep ramp. And we're coming from a point of just within the last year, we've made certain that the core technology actually do work. So we know we have a battery that functions. We know this thing can be scaled. It's a question of execution. But what we're aiming for is the larger scale applications initially, which means grid scale. It means large commercial. However, the core technology is suitable for essentially anything stationary, possibly possibly with the exception of pure battery backup applications. Perhaps, say, if you've got a data center where you're just really only concerned about cycling the battery in the event of a power outage that may hit you every couple months or something like that. You could use our battery for that, certainly, yes, but it's probably not as economical and not as advantageous as something else.
I'm curious, kind of taking this back to the beginning. You said the space program used these batteries, but you found a way to make them more efficient, making these batteries a lot less expensive. Have you talked to the space program about using your version of these batteries?
No, yeah. It's somewhat ironic that our technology was conceived for outer space, but 30 years later, it probably would never be used again in outer space just because it's heavy. In fact, there was a SpaceX mission back in July of last year, of 2020. I went to the International Space Station, and one of the things they did was replace those original nickel hydrogen battery packs with lithium ion packs after 30 years. So they served their purpose for nearly 3 decades. But the cost of putting something into outer space, anything that's heavy, and we expect will always be substantially heavier than a lithium ion solution, you wouldn't want to send us into outer space. It's just a bad use of that precious weight resource.
Expensive lift costs, right?
No, yeah, it would not be worth it. Yeah.
At the time of this recording, it was announced that you received a $12 million investment to get started. What are the next steps, and what are you going to do with that initial round of funding?
Yeah, what we're using that for, and it's actually expanded, I can't give you the specific numbers, but we've been using that to prove the technology, to make sure that the core chemistry with the new material, specifically the new catalyst, does indeed work. And we reached that point roughly in December. We had set for ourselves a set of benchmarks that we thought we needed to hit in order to be competitive in the marketplace. What we quickly realized last fall was that virtually on every measure, round trip efficiency, cycle rate, temperature range compatibility, capacity for energy density in the form of kilowatt hours generated per vessel, as we call it. On all of those, we were exceeding not only the expectations that we had for ourselves of where we needed to be competitively, but also the performance of the legacy nickel hydrogen batteries, meaning that the new materials that Professor Shui and his team came up with actually perform better than the incredibly high cost materials that we were replacing. Instead of trading cost for performance, we ended up getting better performance at orders of magnitude lower cost. And then perhaps most importantly, around December, January, we recognized that some of the metrics we're hitting, the most important ones such as capacity, were actually almost 2 years ahead relative to where we thought we'd be in our business plan. So we're in the process of accelerating our business plan massively and are now in the process of taking the vessels. That's our basic building block. We've purchased a pilot tooling line that lets us do the manufacturing of our batteries with automation, et cetera. And we're installing that in the next few months here and then scaling up very, very rapidly. It's exciting times for us.
Yeah. And so is your business plan to be the sole manufacturer, or would you be licensing it out and someone else would be manufacturing the batteries? How do you see that?
Yeah, we're going to own it. We're in discussions with multiple partners that want to participate as, I'll call it, closely tied manufacturing partners, but it's not a licensing agreement. We want to be the provider of these types of batteries for renewable industry use around the world. We're designing them to be compatible with the standard power electronics that you'd find, meaning the 1,000 volt class and 1,500 volt class inverters and power conditioning systems out there, as well as with standard energy management system software interfaces that we find around the world. But our goal is pure and simple battery supply with this unique, stationary, ultra durable, ultra flexible battery here for the world.
Tell me about where you're planning on doing the manufacturing. One of my first guests was a company called Alivo that was based here in Charlotte, and they bought an enormous former cigarette factory. Just the landscaping alone to keep that place up must have eaten them alive, and they didn't last much longer, but hopefully you haven't bought an old cigarette factory.
Yeah, no, it's interesting what the possibilities are in today's world, and who knows what the new incentives that are being talked about here with the Biden administration coming on board might bring. Our strategy is pretty simple. R&D and pilot line manufacturing is here in the San Francisco Bay Area in Fremont, California, and will likely stay there. As with most power-related technologies, a huge percentage of the research and development and the technical advances are in the actual manufacturing and how you scale this thing up. So we'll keep that close to the vest. That'll be here. From there, our manufacturing splits splits into a front end, which is the electrode manufacturing, and a back end, which is the assembly process that assembles the electrodes, the separators into the vessels, and then ultimately turns that into a battery pack. All of that combined is a relatively modest tooling cost. So if I compare it to the solar industry, which is what I came from, making our battery from scratch, the entire process is analogous to just the module assembly, meaning taking solar cells and making those into panels or modules process, as opposed to, I would compare lithium ion to be analogous to creating solar cell fabrication, which is far more expensive and longer lead times and much more capex, et cetera. So we've got a relatively simple process, a simple assembly process. Again, we think it's on the order of 1/5 of the tooling capital cost relative to equivalent volume lithium ion. And I keep pointing to lithium ion just because I think that technology, given the scale and the head start they have across other things, will continue to set the market price. And we're convinced that we need to be able to match them on a capex basis and win based on the unique capabilities and the levelized cost advantage that we provide because of the maintenance cost savings.
York, I love talking about these kind of technologies because, look, I think they all have a place that doesn't really wipe out the other technologies. It just, this fits here, right?
That's right.
York, I'm going to finish with a lightning round of your thoughts on different energy technologies, starting with natural gas.
I think natural gas is in for tough times. I think the word is starting to leak out that the carbon footprint impact of natural gas, with methane essentially being 25 to 85 times as potent a greenhouse gas as carbon dioxide is, it'll be tough slogging.
Crude oil.
Dinosaurs were around for a long time, but I wouldn't see a lot of demand going forward. Just take a look at what Total, with Chevron, with Shell, what all the big oil companies are doing to make serious inroads into shifting from liquid, i.e. oil, to power and renewables specifically.
Nuclear.
You need to bring the cost down, but it's probably the most promising form of true baseload generation that we'll need. So I think we can expect to see more nuclear, hopefully at a more attractive cost point. I think new renewables beats new nuclear by any measure you can think of, orders of magnitude. So there's a long way to go there.
Coal.
Hard to imagine a whole lot more coal coming on board now that renewables, especially solar and wind, even coupled with storage, beats the marginal cost of operating coal assets in most places in the world. That's a tough sell.
Wind.
I think we'll see lots and lots more wind. I think offshore wind, once the levelized cost of that comes down, will be a significant growth area because of the additional capacity factor and the kind of the timing of how that asset works. But the cost needs to come down, but I think we'll see a lot of it.
Solar.
Solar is the no-brainer. One of my former board members in my last company, I asked him what he thought the cost would be. He says, hard to tell what it's going to be next year and 5 years, but in the long run, it's zero. And I think he was right, meaning that the marginal cost of solar asymptotes to zero. So we're entering an era where electrons essentially are free. It'll be a question of how do you store and capture them and put them to use when you actually need it.
Biofuels.
That was the big promise a decade ago. I think we all thought that cellulosic, ethanol, et cetera, was going to make a big play. Hard for me to see how that's going to gain a lot of traction, but who knows? Might be surprising.
Hydroelectric.
I think basic mechanical storage, whether it's hydro or some of the other forms of long duration play that are mechanical, what Energy Vault is doing, for example, will have a place. And there's some interesting things happening with, say, underwater hydro or compressed air underwater or trying to replicate hydro. I think there'll be interesting use cases where that pencils. The challenges are efficiency. It's a beautiful thing where it works. And I think we're going to find companies that are able to apply it in places where you would not expect it to otherwise work.
Geothermal.
It looks like geothermal is having a renaissance here, and I expect that we'll see that work well, particularly in the climates that have a dark winter period. It's another one of these things where you've got the mechanical challenges of liquids flowing through pipes. It's a bit more complicated, but I think there's definitely a place for it.
You guys, energy storage.
Yeah, batteries everywhere. So I think we're going to see batteries, large and small, of all different types across the entire energy value chain. And probably perhaps the biggest impact will be, I think, the energy grid as we've known it for the last 100 years, maybe 150 years, is going to change dramatically as a result of all that storage coupled with renewables, looking at the transmission and distribution node congestion issues, solving those with batteries, and then look at distributed generation and storage at the customer side of the equation behind the meter. All of that's going to turn our grid upside down. And again, it's hard to predict what it'll look like, but it's going to be very, very different. And I happen to believe that we're at the beginning of perhaps the single biggest economic transition we'll see in our lifetimes, I think even bigger than the internet. And the key to both making it happen and how it shapes the future will be energy storage.
Electric vehicles.
Yeah, electric everything is what we're going to see. All the future carbon footprint reduction models I see begin with electrify everything. And I think we'll see an adoption of electric vehicles far faster than we're predicting today as that begins to take hold.
Energy efficiency.
Efficiency is still generally the best return on investment for a customer. I think the return is about 3 years for most energy efficiency projects. So that's a no-brainer.
And then finally, fusion power.
Yeah, who knows? I'm the wrong guy to ask. I think fusion's been 10 years away for my entire lifetime and appears to be no different. I'll be thrilled if it happens, but let's plan on the others.
All right, Jörg Heinemann, EnerVenue, thank you so much for your time.
My pleasure. Great to be with you, Jay.
That was Jörg Heinemann, CEO of EnerVenue, a metal hydrogen battery developer based in Fremont, California. I want to thank Jörg for his time as well as Kyle Peterson at Clement Peterson for setting this up. You can find plenty of pictures for this episode on energy-cast.com as well as on Instagram and Parler at Host Energy and Twitter at Host Energy Cast. All guests are sent the raw and completed audio the week of release. So far, no complaints. Be sure to leave us a positive review on iTunes. That gets the word out. Music was produced by Sean Stroop at Stroop Loops. That wraps up episode 111. Be sure to join us next week when we explore a new technology for beaming a lot of energy across long distances. Until then, I'm Jay Downhauer. We'll see you next time.